We present clustered principal components for precomputed radiance transfer. The technique produces shadowing, interreflection, subsurface scattering, and complex reflectance effects from dynamic lighting in real time. All images were recorded in real time from a PC with an ATI Radeon 9700 graphics card. We begin with a review of precomputed radiance transfer, or PRT, from previous work. For diffuse objects, a 25-component transfer vector at each mesh vertex captures global transport effects. Correct soft shadows are generated in real time as the model moves and the lighting changes. Arbitrary low-frequency lighting environments are handled with performance independent of the number or size of light sources. PRT was also applied to glossy objects, including isotropic and anisotropic BRDFs. This yields view-dependent shading, but a 25 by 25 transfer matrix is required per mesh vertex, slowing performance drastically. Our method, called clustered principal component analysis, approximates this glossy transfer signal to obtain real-time performance. We show performance and accuracy by switching between the original signal and the CPCA encoded version. CPCA groups high-dimensional transfer matrices into a small number of clusters. Each cluster is approximated by a low-dimensional affine subspace by projecting onto a few representatives. We vary the number of representatives per cluster to show approximation accuracy. With more than about 6 representatives, the approximation gets very accurate. This reduces per vertex storage from a 25 by 25 matrix to less than 10 scalars. Besides accelerating glossy rendering, encoding with CPCA also allows higher frequency lighting on diffuse objects in real time. We gradually increase the frequency of source lighting from a 5th-order spherical harmonic projection to a 10th order. Note how shadows are lengthened and sharpened. We end with more examples of real-time rendering with CPCA encoded transfer. In this example, a glossy head statue model is illuminated by the Grove lighting environment. This glossy Buddha model has precomputed shadows and interreflections. We switch between uncompressed and CPCA rendering, so you can see the performance difference. This translucent skull model is rendered using purely diffuse transfer. It is obtained by simulating subsurface scattering in the transfer preprocessing. Finally, this translucent Buddha model includes both subsurface scatter and a glossy reflectance term. Realistic shading results are obtained in real time as the object, lighting, or view moves.